Hi everyone, welcome to Chapter 7, Mass Wasting or Mass Movements, where we'll talk about things like landslides, debris flows, mud flows, and lahars. I hope you enjoy. In this short lecture, we'll talk about the definition of mass movements, types of mass movements, classification schemes, causes and mitigation efforts, and then I will talk briefly about one of my favorite examples, although tragic, is the Vajont disaster in Italy, because it highlights a number of different elements related to mass movements and human causes of mass movements. A mass movement is anything that is a large quantity of rock set in motion all at once, and that can happen in a lot of different ways. So here's the classification scheme that I like to present to students, where we talk about the speed of motion, which is on the vertical axis, so you can have everything from extremely slow motion to very rapid. And then the amount of water involved is on the x-axis, which is dry on the left and completely saturated on the right. And then on the right here, this table gives an idea of how quickly these things can move. So anything that's rapid to very rapid to extremely rapid will be on the order of a few miles per hour. Everything else can be very slow, and that can be on the order of feet per year in some cases. So let's start by talking about flows. Flows represent the right-hand side of this figure, so everything that's more than moderately wet. Earth flows, debris flows, mud flows, and lahars. And so what distinguishes those are the speeds with which they travel. So as I said in the previous slide, mass movements that behave like fluids are flows. These behave like flows or behave like fluids because there's lots of water involved. And the friction at the base is not so important, but rather the collisions within the fluid itself are what controls the motion. So you can have a wide range of sizes, anything from very, very fine ash or clay to boulders the size of cars or houses. Moderately wet to saturated, as I showed in the classification scheme, and they can be slow to really, really fast motion. They have many names, as we saw in the classification scheme: earth flows, mud flows, lahars, debris flows, and debris avalanches. Here's a debris flow, and you'll get a sense of how scary this can be, actually. So this is down a street of a city, and you can see the scale of the boulders that are being carried by this thing. And notice it's like stream flow, but has much more momentum because of all of the debris that is being carried. And notice the matrix between the big boulders is very fluid, but it's loaded enough with fine-grained material that it's like concrete, and it can push those boulders along. So there's a lot of damage potential here, and I can't tell what the speed is, but it is not particularly slow. So maybe a car driving down a residential street is the speed of this flow. So as you can see, it's behaving a lot more like a fluid than a solid, even though it has solid chunks within it. Okay, here's an earth flow. This is an interesting example from Russia, and you'll see that there is some fluid behavior, but it isn't necessarily fast. I'm going to mute this in case you can hear the funny music that's going along with it. So you can see this saturated earth is just creeping out onto the roadway. And as you can see, it's pretty viscous, even though it has fluid-like behavior, but it's viscous fluid-like behavior. So let's get another look at that part that's down the road from us. Also, again, you can see there's tons of, there's a lot of momentum here. Look, those trees are just being, knocked down like they're nothing. But you can see in the part that's on the road that it has these lobes. And remember I said in a previous lecture that viscous fluids that contain a lot of debris will tend to form these fingers or lobes at the front. That's a characteristic of viscous fluid flow. And you can see that this thing it's hard to see exactly how much water is involved, but it's behaving like a very viscous fluid system. Okay, one thing to think about in flows is that they tend to have long runouts, and that means that the height from which they fall over the distance over which they travel is low, meaning their runout distance, L, is long relative to the height that is traversed. So rock falls and small volume avalanches tend to have an H over L of 1/2, meaning their runout distance is twice the distance that they fall from. But if you increase their volume, then you can get an H over L of 1 over 25, meaning the distance over which they can travel horizontally is 25 times greater than the drop, or the distance that they fall downhill. So this is a classic measure of mobility, H over L. And so 1 over 25 is a very, very mobile debris flow, or very, very mobile flow of any kind. There are massive rock falls that are really fluidized, and they can have very low H over L's or very large L's compared to H, and they're called Sturströms. It's a very difficult German word to pronounce. Now let's talk about slides. This is where these things don't really behave like fluids, they behave like solids. So they sit right in the middle of the figure. They're sort of anywhere from kind of moderately wet to possibly a little bit dry, and they have moderate velocities. So a lot of times they can happen at the plane between two rock units. So in this cartoon from your textbook, you can see that the surface of the slide, the basal surface of the slide, is between that lighter unit and the dark unit. And so sometimes stratigraphic boundaries in rocks can create some kind of weakness and a slide surface. So that can be due to the presence of clay, which we'll talk a little bit about later, or they could be due to just simply a break between two units that offers an opportunity to sort of have a gap and there's no cohesion between those two layers. Here's an example of this happening on a road cut. And remember I mentioned that road cuts are a place where these kinds of things happen all the time. Notice that it's happening along, I think, a bedding plane. So it's sort of at the gap between two stratigraphic units that's sliding. And this is also daylighted bedding. So remember that when I mentioned daylighted bedding later in this section. Uh-oh. Oh dear. So it seems that the slide occurred sort of parallel to the bedding plane, and probably the surface of the slide was at the gap between two units within that sequence of units in that rock outcrop. You can also have similar kinds of things happen which are not necessarily at the stratigraphic divide between two units. They can be more complex than that, especially if the geology is complex. And the surfaces may be, rather than a flat surface, could be curved in the way shown here in this image from your textbook. Okay, so now we're going to go to the top left of this figure, which is the fastest and driest of all of the mass movements. And these are rock falls. And so this is where you have often a shear face that lends itself to gravity just taking over. Uh-oh. That was human caused, but it probably would have happened anyway. And luckily no one was below there, because I noticed other people not very far away. Okay, on the other end of the spectrum is creep. And creep is the slowest and somewhere between dry and moderately wet. So this is the kind of thing that you may have seen before. Have you ever noticed on a hill slope that trees are curved like these trees in this image? Or that electric poles are tilted in one way or down slope? And so this is something that happens over very long time periods, and that's why it's called creep. And so I'll show you a few slides of explanation. So what happens is that it's a very slow process that happens more or less seasonally, and you don't really notice it until you start getting trees that are curved or electric poles that are tilted downhill. So if you have your hill slope, as in this right image, in the winter months, it will freeze. The water that's in the interstices in the soil will freeze, and that will expand the surface upward, perpendicular to the surface. But then in the spring, when there's a thaw, that sort of collapses downward, but instead of collapsing back along the same vector that it came from, it will collapse down vertically, which is slightly angled from the expansion direction, and it will always be sort of inching its way downhill. So one season you have an expansion perpendicular to the slope, and then your thaw and contraction is in the direction of gravity. So it starts to move the whole surface downhill, and then it expands again, and then it contracts. And so over season after season, this will start to have this motion of the surface of that hill slope moving downhill.